On this video, we're going to focus on projectile motion of vectors. First of all, let's talk about the general formula for ideal projectile motion and what does it mean. When we shot a projectile, we shot it with an initial velocity. If we think of our vector, that initial velocity would be our magnitude of the velocity. Okay, so that projectile has two components, which is the horizontal and vertical component, just like vectors do have those two components. To calculate the horizontal component, we use the formula, the magnitude of the velocity times cosine of the angle. Okay, that will give us the horizontal component. And then times some parameter t. Okay, so after 1 second, after 2 seconds, after 3 seconds, after 4 seconds, it's going to calculate and basically the horizontal length of the projectile. This is going to give us the vertical component. Now you see that the vertical component has the same as what we talked about before for the vertical component of vectors, which is the magnitude times sine of the angle times the time, of course. But then it has an extra component because when we shot a projectile, there is resistance, and that resistance is called the gravity. The gravity is acting on the object and is pushing it down. So that's why we have minus 1/2 gt squared. That is the force of gravity acting on the object, pushing it down. So this is going to give us the, including taking resistance into consideration, it will give us the vertical, the vertical height of the vertical component of the vector, of the vector, yes. So now there's a couple of more things that we can do, and one of them is we can talk about the maximum height that the object is going to reach. Okay. Now the maximum height is going to happen exactly at the moment that my vertical velocity is going to be 0. Okay, it's going to reach the maximum height once the velocity goes to 0, right at the top, at the very top. So, but we're just talking about the vertical component. So I'm just going to say I'm going to take the vertical component, which is we're going to call it the y, right? So that's my y component. But again, I'm going to put it in terms of y, y sub t, because it's in terms of t. Right, that's my vertical component, and that's going to give me the initial velocity times sine of an angle times the parameter t minus 1/2 times gt squared. Now we said that the maximum height is going to happen when the velocity is going to be 0, right at the top. So what we're going to do here, I'm going to make a little modification. I'm going to get the derivative of this function, and that's going to give me the vertical velocity, v of t. I'm just going to call it v of t. And we're going to find the derivative, of course, is with respect to t. So the derivative, this is just a constant times t, right? The derivative of a constant times t is just going to be this constant, which is v sub 0 times sine of the angle alpha. Minus the derivative of this one would be 1/2 g times 2t, right? Because this is just a constant. So my velocity, vertical velocity is going to be v sub 0 times sine of alpha minus, this can simplify, so we get gt. So and then we want to find the time when the velocity is equal to 0. So we can find that vertical maximum height. So I substitute the 0 into the velocity and solve for t. This is going to give us the time that the velocity is going to be 0, which is going to be the same as our maximum height. That's when the velocity is 0. Okay, so we solve for this, so that's going to give us gt equals to initial velocity times sine of alpha. And then we solve for t by dividing by g. So t equals the initial velocity times sine of alpha divided by the gravity. Okay, so this is the time that is going to take for the projectile to reach its maximum height, because that's when the velocity is going to be 0, right there, on the y component, right? Because we're just using the y component. Okay. Now I'm going to substitute this. So if I want to find the maximum height, so we're talking about this, y equals, the y component is given by this part of the equation, right? So I'm just going to say y equals to b sub 0 times sine of alpha times t minus 1/2 gt squared. But the maximum height happens when t is equal to b sub 0 times sine of alpha divided by g. So at that t is when the maximum height is going to happen. So we have the initial velocity times sine of alpha times the time that is going to take to have a velocity of 0, which is going to give me the maximum height in that particular case. So the initial velocity times sine of alpha divided by the gravity minus 1/2 times the gravity times the time squared. But the time again that it takes for it to reach the maximum height is the initial velocity times sine of alpha divided by the gravity. If we simplify this, this is going to give us the maximum, a formula, a simpler formula than the one we could find for the maximum height. Okay, so this is going to be b sub 0 times sine of alpha times b sub 0 times sine of alpha is b sub 0 times sine of alpha squared divided by the gravity minus, now right here, if I square that on the other side, it's going to be b sub 0 times sine of alpha divided by the gravity squared is just going to be b sub 0 times sine of alpha squared divided by the gravity squared. The gravity simplifies with gravity right here, so we're going to be left with the following formula. The maximum height is going to be the initial velocity times sine of alpha squared divided by the gravity minus the initial velocity times sine of alpha squared divided by twice the gravity. You see, we have 2g on this one. So if I want to have the same, combine these two fractions, I need to have the same denominator. So I'm going to multiply this one times 2, and we're left with this formula that the maximum height is given by twice the initial velocity times sine of alpha squared minus once the initial velocity times sine of alpha squared, which is going to be just one initial velocity times sine of alpha squared divided by the denominator, which is 2g. And that is an additional formula for us to be able to find just if we were looking for the maximum height that the projectile is going to reach, and this formula is always going to work. Okay, so that formula is given right here. Now, from this we can derive another formula, okay? And that other formula is that we can find the flight time. What does it mean by the flight time? How long is it going to take for the object or for the projectile to strike the ground? Okay? And for the strike time, we can also, the projectile is going to strike the ground whenever, what is it called? Whenever the velocity, it is equal to 0. It strikes the ground also. Okay. Or, yes, that we can use it like that, or we can say another thing. It also happens when the height of the object is also 0. So that's another case. We can also think of it as the height of the object. Okay, so I'm gonna use the second one, to derive the formula. So we know one thing, that this represents the height of the object, right? Which is my vertical component. So the time is gonna take to get the total flight of it. The total flight of the projectile is when that height is gonna get to 0, when it's gonna strike the ground, right? So I'm gonna put that formula. So that is my height, right? I'm just gonna call it the y, and it's b sub 0 times sine of alpha t minus 1/2 gt squared, right? So, and the total flight time it's going to happen, it's going to whenever it strikes the ground. So from the beginning to whenever it strikes the ground, and it strikes the ground when the height is equal to 0, when this value of y is 0. So you see right here, I'm going to treat this equation as if it was a quadratic equation, okay, because we have t and we have t squared. So I'm going to fix it so you see it as if it was just a regular quadratic equation. I'm going to put the square first. Negative 1/2 gt squared plus the initial velocity times sine of alpha t. So this is like the same as saying, let me just highlight some stuff here for you. This is like ax squared plus bx. And then you see that there is no c. That means it is a plus 0. So we're going to treat it as a quadratic equation in which this is a, this is b, and this is c. So we can use the quadratic formula to find the time that it takes for this object to hit the ground. And that is going to give us basically the time that it's going to take for it to cover the total distance, which is going to help us calculate the flight time. Okay, so using the quadratic formula, t equals negative b plus or minus, it's not x, it's the time, the square root of b squared minus 4ac divided by 2a, right? So that's going to give us negative b, which is b sub 0 sine of alpha, plus or minus the square root of b squared, which is b sub 0 sine of alpha squared, then minus 4 times a, which is negative 1/2 g, times c, which is 0. Everything is going to be divided by 2a, and 2a is negative 1/2 g. If we simplify this, we're left with negative b sub 0 sine of alpha plus or minus. Now you see that all of this is going to give us a 0. Right? So we're just going to be left with b sub 0 sine of alpha squared, and then the square root of that is just going to give us b sub 0 sine of alpha. Everything divided by 2 times negative 1/2 g is just negative g. So the time that it's going to take to hit the ground is going to be negative b sub 0 plus or minus b sub 0 sine of theta divided by negative g. What if it is a plus? If it is a plus, that would give us negative b sub 0 sine of theta plus b sub 0 sine of theta divided by g. So I'm going to put both of them so you can see. Sine of alpha, not theta, plus b sub 0 sine of alpha divided by g. And the other case is, what if it's a minus? C is equal to negative b sub 0 sine of alpha, well, it's negative g, minus b sub 0 sine of alpha divided by negative g. Look at the first case. Negative b sub 0 sine of alpha plus the initial velocity sine of alpha is going to be 0 divided by negative g, which is 0. What does this tell us? This is the time at which the projectile was launched, which is at 0 seconds. We're not interested in that. We're interested in when it hits the ground, the time that it hits the ground. So that's going to be given by this one. Negative initial velocity sine of alpha minus initial velocity sine of alpha is negative 2 initial velocity sine of alpha divided by negative g. So the time that it takes to hit the ground, it's going to be negative over negative is positive, so twice the initial velocity times sine of alpha divided by the gravity. Okay? So this is the time that it's going to take to hit the ground. So now if I want to calculate the flight time, I just want to know what is the horizontal distance that the projectile is going to cover, and that is only given by the x component of the position vector, of the position of the projectile, and that x component is given by this formula, the initial velocity cosine of alpha times t. Okay, so but we want to find the position when the time when it hits the ground, right? So that's going to be when the time is equal to twice the initial velocity sine of alpha divided by the gravity, right? I want to find that position. So it would be the initial velocity times cosine of alpha times the time, which is going to be twice the initial velocity sine of alpha divided by the gravity. And if we simplify this, that's going to give us twice initial velocity times initial velocity will be initial velocity squared times cosine of alpha times sine of alpha over the gravity. And look at this. This is going to be something particular that you have seen before in pre-calc. It is one of the formulas for pre-calc. Look at this. 2 sine of alpha cosine of alpha is the same as sine of 2 alpha. So that would be the same as the initial velocity squared divided by the gravity times sine of 2 alpha. This formula is going to give us what we call the flight time. Okay, it's going to calculate for us basically the distance, you know, the horizontal distance that it's going to cover, that the object is going to cover. Okay, well, the flight time, first of all, we found it through the first, well, that's not the flight time. The flight time is the time. So that would be the range. So I'm gonna fix that. The flight time was given by the time that it takes to hit the ground. How long is it going to be on the air? It was given by this. Okay, so that is the flight time to begin with. Okay, I'm gonna put this flight time. This that we found right here is the distance that is going to take that is going to cover until it strikes the ground from beginning to end. That we're going to have a different name for that. That is going to be the total horizontal distance, which we call it the range. What is the range from the beginning to the end? Horizontal distance. And that is given by just whenever at the time that it strikes the ground, how much horizontal distance the object is going to cover. That is given by this formula. So, summary. These are the three formulas that we talked about. Maximum height, we can find it through this formula. The time that it's going to take for the object to hit the ground, basically how long how long is the object is going to be in the air, and this is the range, which is how much horizontal distance is going to have covered about from the beginning until the time it strikes the ground. All right. Let's start with this problem here. It says a projectile is fired with an initial speed of 600 meters per second at an angle of elevation of 30 degrees. Answer parts A through D below. When will the projectile strike the ground? That would be basically the flight time. How long is it going to be in the air? That's what it's asking. Okay? And the flight time is given by this formula. 2 times the initial velocity times sine of alpha divided by the gravity. 2 times the initial velocity times sine of alpha divided by the gravity. Now, this is going to be 2 times the initial velocity, which is 600 meters per second, times sine of alpha. Sine of alpha is the angle that it was at which the projectile was shot. It was shot at an angle of 30 degrees with the horizontal. Over the gravity. The gravity in meters per second, it's going to always be 9.8 meters per square second. Per second squared. Now, if the gravity, you have it in feet per second, that would be 32 feet per second squared. Okay, so in feet per second, it would be 32. So, let's go ahead and evaluate this using the calculator. So that would be the last part we have to do. So it would be 2 times 600 times sine of 30 degrees. And make sure the calculator is in degrees in the first place. We need to make sure it is in degrees. And this is going to be divided by 9.8. So the flight time is going to be 61.2 seconds approximately. So that means that this projectile is going to be about 61.2 seconds in the air until the time that it strikes the ground. Okay. Why is it seconds? Very simple, because the formula for this, it would be 9.8 meters per second, and you see that meters per second simplified, and you're left with seconds. Okay, which is the unit of measure that we're using here. Okay. Now, second question here is asking, how far away will the projectile strike? Basically, it's asking for the range, the horizontal length that is going to cover until it strikes the ground. So that would be the second question here. So let's find the range. To find the range, what do? Let's use the range formula, which is initial velocity squared divided by the gravity times sine of twice alpha. Initial velocity squared divided by the gravity times sine of twice alpha. So that is going to be the initial velocity, which is 600 squared divided by the gravity, which is 9.8, times sine of twice the alpha, which is 2 times 30. And that should give us the range, the horizontal distance that this projectile is going to cover. Okay. Another way that I could have done this, you see that it takes 61.2 seconds for the object to strike the ground. So I could also have gone to the original formula, which is this one for the projectile, and I just want the horizontal distance that is going to cover. So I could have used the horizontal component of the position, which is the initial velocity times cosine of alpha times t, and when t is equal to 61.2 seconds, and that should have given us the exact same thing. So let's try it both ways so you can see that we would get the same answer from either formula that we use. Okay, first of all, let's solve it through the range formula that we were given. So 600 squared divided by 9.8, and that is going to be multiplied times sine of 2 times 30, which is 60, right? Oh, I put an extra parenthesis, and that gives us 31,813, like approximately 31,813 meters. 31,813 meters. Okay, so it will strike the ground like after it has covered this much distance, horizontal distance. Now, if we would have used the horizontal component of the position, we can also find how the length of the travel by just substituting the time, because this is the time that it takes for it to hit the ground. So this is the end of the travel at 61.2 seconds. So all I need to do, substitute the t with the 61.2. So the initial velocity is 600 times cosine of the angle that it was shot at. It was shot at 30-degree angle times the time, which is 61.2 seconds. That should also give us the range, or the position, or how long is it going to have traveled after 61.2 seconds. So that would be 600 times cosine of 30 degrees, and that times 61.2 seconds. That would be 31,000. You see that it is not exact because we rounded the time to 61.2. If you use 61.2244898, which is the exact time, you will see, let me just extend it so you can see. It was going to give us a closer approximation to the length of the flight time, which is 31,813 meters approximately, is the same answer. Okay. So whatever formula we use, again, we have several options, but these are shortcuts These formulas that I just provided that we derived from the original formula in the lecture, so that we can use to actually also come up with the solutions. Okay. Now, C, it says, how high overhead will the projectile be when it is 5 kilometers downrange? What does that mean? When the horizontal distance, it is at 5 kilometers. Okay, so how high will the object be when the horizontal distance, it is at 5 kilometers? What we need to do, go to the horizontal distance formula that we have right here. We can use that one. Okay, let me just put it here. Same formula, horizontal distance. Okay, and first thing that I'm going to do is I'm going to find the time that it's going to take for it to be 5 kilometers like horizontally. So when the position is at 5 kilometers, but since the formula is in meters, so I need to turn it to meters, so it would be 5,000 meters, because each kilometer is 1,000 meters, right? So 5,000, the initial velocity is 600 times cosine of the angle, which is, it was shot at a 30-degree angle, and all we want to do is find the time that it takes for it to get to that 5,000 meters, to those 5,000 meters horizontally. So I'm going to solve for t. It's just going to be t equals to 5,000 divided by 600 times cosine of 30. That should give us the time that is going to take for it to get to that horizontal distance of 5 kilometers downrange. So we got 5,000 divided by 6. I'm going to put it in parentheses. 600 times cosine of 30, close the parentheses, and it gives us about 9.622 and so forth. I'm just going to copy the whole number so we don't round yet until the end. Okay, so this is basically the approximate time that is going to take to have covered a horizontal distance of 5 kilometers, which is my 5,000 meters. But now the question is, how high will the object be at those 5,000 meters? So to find the height, now we're going to go to the vertical component of the position. Okay, this is our vertical component of the position. This is what we're going to use next. I'm just going to copy it. Wait a second because it's loading. And there it is. Okay, so now we're going to use this formula for the position. We want to find how high. Remember that this is going to be the position, but it's going to be my vertical position, right? Because it's the vertical component. We want to find the vertical position when the time is equal to 9.6 seconds. Okay? So that's what we're going to do. Vertical position when the time is about 9.6. Oh, I'm just going to write the whole number. 9.622504486 seconds. Initial velocity is 600 times sine of 30 degrees times the time, which is 9.622504486 minus 1/2 times the gravity, which is 9.8 meters per second times the time, which is 9.622504486 squared. And that should give us the horizontal distance the vertical distance that is going to be at, the height at which it is going to be whenever it reaches the 5 kilometer range. Okay. Let's put that in the calculator so we can find that. So it would be 600 times, I'm just going to put it in parentheses so we can follow this, 600 times sine of 30 multiplied times the time, which is, I'm just going to put the answer from the previous because it saves that answer here, so that way I don't have to write the whole thing, minus 1/2 times the gravity, which is 9.8, times the time, which is the answer that I got, squared. And that gives us 2,433. So that means that it is going to be at a height of 2,433 meters approximately when it has covered 5,000 kilometers, 5,000 meters, which is 5 kilometers horizontally. The projectile is going to be at this height, 2,433 approximately meters high. Okay, that's the answer for letter C. Now let's go to letter D and last. What is the greatest height reached by the projectile? So we need to find my Y max. And that we found a formula for that. The maximum height is given by this formula. Initial velocity times sine of alpha squared divided by twice the gravity. Okay, so initial velocity would be 600 times sine of 30 degrees squared, and that is going to be divided by twice the gravity, which is 9.8. And it is in meters, so my answer is going to be in meters. So let's find the approximate, what is the maximum height that the actual object is going to reach. So 600 times sine of 30, that is being squared, and then divided by twice the gravity, 2 times 9.8, close the parentheses, and this is the maximum height, 4,591, which is about 4,592 meters. So those are all the different answers that we found from this problem. Let's just work on another projectile motion problem, and then we're going to stop right there on this short video. Next. An athlete puts a 16-pound shot at an angle of 30 degrees to the horizontal from 6.5 feet above the ground at an initial speed of 45 feet per second. How long after launch and how far from the athlete does the shot land? For this part, for this problem, there is going to be a little modification to our original formula. Let me go back and I'll explain to you why. This is my position of the projectile, my original position. However, on this problem, we cannot work it out the same way. Hold on. This is stuck. Okay. On this problem, we cannot work it out the same way because the position, it is not starting from the standard position. It is starting from 6.5 feet above the ground. So I have a different formula for you, just a little modification of the position formula, which would be for the x component, if it is not starting from some initial position, then we're going to say it's starting from some x of 0 value plus, and then my initial velocity times cosine of alpha t I. And the same thing with the vertical position. It might be starting from some y of 0 as my initial position plus, and then my b of 0 times sine of alpha t minus 1/2 gt squared j. Okay, so let's go ahead and continue. Oh, just one little thing on this x of 0. So that's separate from the t. So this is the one that is separated. All of this is my I component, but I just the t just goes along with my horizontal length that is calculated by the magnitude times cosine of alpha. Okay, this is just an additional value that will be added to it. depending on where it starts. If it starts from somewhere on the left side, on the right side, you know, whatever is it that the starting position is. Okay, so on this problem, we are given that my initial x value, it is starting from the standard initial x value of 0. So it doesn't say that it has been moved to the right, to the left, or anywhere. Right? So I'm just going to be putting that information. So that's going to be 0. So I don't need to worry about that. So the initial velocity, it is 45 feet per second. So it would be 45 times cosine of alpha, which is 30, times t, I. This is going to be my I component, which is my horizontal component. Okay? Plus, then my initial y value, it is starting at a height of 6.5 feet above the ground. That means that is my initial y value for the position. So it would be 6.5 plus my initial velocity, which is 45, times sine of alpha, which is 30 degrees. And then t, right? For this is going to be t, minus 1/2 times the gravity. Now, right here, since the gravity we need to use, since it is in feet per second, it is in feet, and it is in second, so we need to use the gravity in feet per second, which is 32. That's the gravity as feet per second, not in meters per second anymore. So that would be 32 times t squared, and that would be my j component. So I'm just going to simplify this. So the position is going to be given by 45 cosine of 30 degrees t I, that's my I component, which is my horizontal component, plus 6.5 plus 45 times sine of 30 degrees t minus 32 times 1/2 is going to be 16 t squared, and that is my vertical component, which is my j. Okay, so what do we know about, once again, it is asking how long after launch and how far from the athlete does the shot land. The shot lands when the height is 0. So that means when this vertical component, it's going to land when this vertical component is equal to 0. So we're going to say we want to find the time that it's going to take for this height to become 0. And you see that this is a quadratic equation, ax squared, so this is my a right here, plus bx, this is my b, plus c, that is my constant. Ax squared plus bx plus c equals to 0. So using the quadratic formula, we're going to solve for t. So t equals, okay. Now we cannot use the original formula for the flight time because in this one we have an initial, it is not shot from 0. It is shot at a height of 6.5. So we need to go through the whole process that I went through at the beginning to find the time using the quadratic formula. So it would be negative b, which is going to be 45 sine of 30 degrees, plus or minus the square root of b, which is 45 sine of 30 degrees, squared, minus 4 times a, which is negative 1/2. Hold on, I made a little mistake, right? Right here, it wasn't negative 1/2. I'm just looking at it. It is negative 16, right? It's supposed to be negative 16. All right, so I'm going to fix that. So minus 16, a times c, which is 6.5. Everything is going to be divided by 2 times a, which is negative 16. Okay, so let's simplify this. T equals to negative 45 sine of 30. The only thing I can do right here is I'm just going to do it straight in the calculator, this part. And I'm just going to do it with the plus and the minus to see what are the two answers that we're going to get. I'm going to do it directly. Right here I can just simplify that part to make it easier, to make it simpler. That minus 4 times negative 16 times 6.5. 6.5, it is going to give us 416. But it's positive, so it will be plus 416. Okay. Everything divided by negative 32. So now we're going to find the two times using the calculator, the approximated times, one with the plus and one with the minus. And let's see which one is going to be the correct one. One of them is before it is going to give you the time at before it was shot, and the other one is after it was shot. So after it hit the ground. So we want the one after. Okay. So let's go ahead and check it out. So it would be negative 45 sine of 30, and the first one I'm going to do the plus the square root of, then it is going to be 45 sine of 30 degrees but squared plus 416, right? And all of that, it is going to be divided by negative 32. And that gives us negative 0.24 seconds. What do you think that tells us? Okay, I am located at a height of 6.5 meters or 6.5 feet, right? And I'm shooting a projectile from here. But then it's going to hit the ground after some seconds, right, when the height is 0. What do you think that negative 0.24 second means right here in this context? That would be basically, because this creates a parabolic motion, that would be the time, a time that doesn't even exist. It's a time on the parabola where the height was 0, but that would represent the time before it was shot. So that's why it's a negative time. Right here we're at t equals to 0, right at this position where we're going to shoot it, right? So this is a little bit before. So that one doesn't make any sense, because as part of the context, we're not interested of the time that before it was shot, right? I want the time after it hit the ground, which is whatever time we're going to get for this one. So I'm going to now, instead of a plus, I'm going to do a minus the square root right here, and that gives us 1.65 seconds. So I'm just going to put the whole thing, okay? This is the time that it's going to take for the projectile to strike the ground. It's going to take approximately 1.6 or 1.7 seconds, approximately. Okay. Right now I'm going to put the whole thing, but I'm going to round it to 1 decimal place for right now. Okay. So the time is approximately equal to 1.7 seconds. Okay. That is one of the questions that we were asked. The second question is, how long after launch and how far from the athlete does the shot land? Does it hit the ground? How far from the athlete? That would be the horizontal component. That's what we're looking for. And the horizontal component is given by this formula. That will give us basically how far from the athlete. Okay, it's going to be given by that component. So let's find how far is it going to be from the athlete. So that would be my position, my horizontal position, which is going to be given by 45 cosine of 30 degrees times t. and we want to find that position when t is equal to 1.7 seconds approximately. What I do recommend is that you put the whole time, don't round it. So put the 1.65 to 14279. So we make sure that we get a closest answer. Right here I'm just going to put 1.7, but whenever I evaluate it, I'm just going to put the whole number. So the shot is going to be at this distance from the athlete. 45 cosine of 30 degrees times I'm just going to put the 1.65, which is the answer that I got previously. And so the shot is about 64 feet from the athlete, okay, once it hits the ground. Approximately 64 feet from the athlete. So that would be basically this distance right here, from whenever it was shot to whenever it struck the ground, 64 feet. And that happened after this time, which is a time of 1.7 seconds. Okay. So that gives you a better idea of how projectile motion works on vectors. Okay, so this is going to be the end of this video.